Okay. Today we're going to be talking about, continuing from last time, about nonlinear regression. And I guess to address one point that was made last time in terms of my usage of linear and nonlinear, just maybe put more simply, the functions are nonlinear in the input, but linear in the parameters. So in that sense, it is linear in some sense, but nonlinear in input. And so I'm going to use the term nonlinear to refer to that, even though some people might call this all linear regression or have it fall under that category. Today we're going to mainly talk about kernels, which, as I mentioned last time, are one of, again, the biggest trends in machine learning in the past 15 years. And they offer a way for us to work with very high dimensional feature spaces, things we couldn't even compute, but do it tractably. And so for that reason, they're actually very, very appealing, because we can work with very, very large features, but still keep things tractable in memory, for example. And we'll see how that works. It seems very kind of like magic until you just go through it, and then it's not that big a deal. Then if we have time, we'll talk some about classification as well. And classification is the problem where instead of continuous valued outputs, which is what we have now in regression, we have discrete valued outputs instead. Before getting too much into that, though, I did want to highlight one point I think there was a little bit of confusion on, and probably this confusion came up because of the nature of the examples I've been using thus far. So the question is, I've defined the input as xi, a vector in Rn. So n is the dimension of the input. And the features, which are phi of xi, that is a vector in Rk. So k is the dimension of the feature vector. And there's some confusion about what exactly n was. And probably the confusion comes from the fact that n is equal to, in fact, 1 in most of the examples I've had, so it's hard to really generalize from that. The basic idea is if we have some input, there might be many sort of fundamental things that we want to actually predict our output from. So for example, xi here, say xi and yi, actually I'll write yi way over here, for reasons that will hopefully be obvious soon. But xi in our example, so for example x1 here, was the high temperature for a day, and that's actually all it was. Right? So there was one input, n was equal to 1, and our input was high temperature. The output then was the demand, or peak demand. Peak demand. Which is also one-dimensional. That will always be one-dimensional. But the point is, we actually could have more than just one thing we're regressing on, right? So we also here could, for example, add low temperature. And low temperature is not some feature of our existing input, right? Low temperature would be another input that we would actually have. So here, in this case, n would be equal to 2. And rather than a line to the data would really be in 3 dimensions, right? Because we would have 2 input vectors and 1 output vector, so we have a 3-dimensional graph. And linear regression, or actually any regression rather, would take these 2 inputs, produce an output, and so we'd actually be talking about surfaces in this 3-dimensional space, is what our model takes the form of. For linear regression, these would be planes through the space. The features are something a little bit different. From this input, we can compute any kind of number of features from this. So in the simplest case, linear regression, it was just exactly these things. The phi of xi here. It was exactly these things. So we had high temperature. I'll go with the example where we have both these input features here, so we also add low temperature. And then we also add, just by convention, we add the vector 1 to include for constant terms. And that is k. So k here is 3, and n is 2. Right? Now we can also choose higher dimensional feature vectors here. So for example, an alternative would be the polynomial bases I talked about, or polynomial features I talked about before, and that would have the same ones here. So these would actually still be included. I'll just leave these here for now. And we also have some polynomial functions of these now. In particular, for a degree 2 polynomial, we would have things like high temperature times low temperature, right? We also would have high temperature squared. Maybe I'll put parentheses around these. And we'd have low temperature squared. So here, n is still 2 because we still have 2 real kind of inputs to the system. But k now would be 6 because we have 6, 1, 2, 3, 4, 5, 6 different features we've computed from those inputs. This is maybe a little bit confusing because sometimes the distinction between features as inputs, people don't really make those, right? And an input could be just like a picture, right? And you don't even really think of ever using your picture as input in kind of raw form. You always will go ahead and compute features of those things. And so people just oftentimes think of the features as the inputs. But for this class at least, we're going to think of inputs as being those things which are actually independent variables as we are putting into the system. The features are functions of these things. And then the output is just the real number, or later on the discrete value we want to predict. So does this make sense and kind of clarify what n and k is and those difference there? I realize it's a little bit confusing because we chose n equal to be 1 for all the examples you've seen so far. We'll have n equal 2 in classification just because it's a little easier to draw those pictures. But I'm choosing n equal to 1 here really just because you can really see the picture nicely. You can see the x-axis being the input and the y-axis being the output. And a 3D chart's not quite as easy to visualize. 3D is okay, but 4D is really hard. That starts messing with your head. All right. Any questions about this? Okay. And so actually, let me go back a few slides here. But when I said, for example, that the computational difficulties arose from the fact that if we have a degree d polynomial, then the number of features equals n, our input size, plus d, our max degree of the polynomial. Choose d. Don't worry about this precise form here. This comes out of some pretty simple operations about how many different polynomials you could have here, how many different terms you have, or I guess monomial terms you have here. But hopefully that clarifies exactly what these things mean. It means even for a relatively low dimensional input, so we don't have that many different real inputs we're talking about, if we want to compute all the possible polynomial, or really each one with just a single term here is called a monomial. So we want to compute all these monomial terms. There would be a lot of them, even for reasonably small n, small d, 10, 20 or so. That still gets really big really fast. Right? So that was the problem here, is that even if n and d are maybe relatively small still, k will still be huge. So if we want to compute all those features and store them in a big matrix phi, that's going to be really hard to do. And that was the fundamental problem, the computational problem with big feature vectors. Sorry, with high-dimensional feature vectors. This was separate from the representational problem which is about when you have a lot of features, you may fit your data too closely. That's really a separate issue, which we handle in different ways. But the computational challenge here just comes from this fact that there's going to be a whole lot of features that we're creating. OK, so now let's talk about these kernels and what these are. And it's important to understand that kernels address the first of those two difficulties with high-dimensional features, the computational problem. What kernels allow us to do is to implicitly work with very high-dimensional features, very high values of k here, without ever actually constructing them. That seems, again, kind of interesting, but all the problems we had with high-dimensional features, like the fact that we can overfit our data, that still exists. So we still can potentially have those problems, and we need things like regularization to help prevent that, but we can start to address our computational problems through kernels. All right, so how does this work? How can we possibly, use high-dimensional features here without actually using them, without constructing them? And to give a simple example, I'm going to talk about computing dot products or inner products. All right, so I'll come back to in a bit why this actually helps us. But let's just talk for now about computing dot products. So let's say we have some feature vector. And I'll use z here again to represent the input to our feature vector. Z is going to be in R2 in this example. So this is a feature vector that maps two-dimensional inputs to, in this case, a quadratic set of features. So here, we have two inputs. We have a max degree of 2 for our polynomial features. And these are a set of features. And I'm scaling them by some numbers here that you have to scale them by, in fact. But that isn't that big a deal, right? Because we can just take back that same amount of scaling in the theta parameter, right? So the scalings here don't really matter. That's not quite true when you talk about regularization, because then the scalings matter. But can ignore that for now. First of all, I just want to make it clear that this is just that quadratic feature that I wrote before on the board. So I have two different inputs, z1. Sorry, I have two different inputs, which I'm calling z and z prime. Z prime. And here, in this notation, again, these things vary by your particular usage, but that's just sort of life. Here, z1 will refer to the first element of z, and z2 will refer to the second element of z. Yeah?
Why does the feature vector need a constant term again?
Oh, so right, that's a great question. So let's talk about linear regression again, right? And we have some data like this. So our feature vector is just the data and then a constant term in this case. And the reason for that is if you didn't have the constant term, you would be limited to essentially y equals a of x as your function. With this axis here is x, your input, and this axis here is y. And even though the data lies in a line here, this functional form requires that you have to pass through the origin with any line, right? So any line would have to have the point x0 equals 0. That's not a very good predictor, right? Because there's no reason for that. You can still fit a line like this and have it still be on a line and have it still be linear. The input's still a linear function of the data. The output is still a linear function of the input. So it's all linear. But it's definitely nice to actually add, again, kind of in single dimensional notation, it's nice to add this intercept term here. So the 1 term in the feature vector lets the corresponding theta term, because remember our output really is equal to theta transpose x, which equals really theta 1 times the first feature plus theta 2 times the second feature. And so whichever one is 1, I'll just say this one is 1. Theta 2 there acts as our intercept term for this line. And that's true even when you have quadratic features, you still would want that, probably. You wouldn't want these to have to pass through the origin. Does that make sense to everyone, that issue there? OK. So I have these two inputs, z and z prime. And I have this feature vector here that I've defined. This is a quadratic feature vector. So it's a polynomial with degree, max degree 2. And let's just say, for reasons that will become clear shortly, that I want to compute the inner product of phi z transpose phi of z prime. So I'm not talking about, it's a little bit of a digression, but I'm not talking about really computing high-dimensional features. I'm just saying, if we have some feature vector here, let's talk about computing its inner product with another feature vector. So we can write it out. And I'll just write this out exactly, but show how all these terms kind of multiply. I'm just going to multiply. Remember, the inner product here is just the product of these two plus the product of these two for the corresponding feature vectors plus the product of these two, etc. So I'm just going to multiply the corresponding entries for z and for z prime. So that equals 1. 1 times 1 is 1. Plus 2 z1 z1 prime. That's this entry here. And the 2's, square root 2's multiply, so you have 2 in the end. Plus 2 z2 z2 prime. That's this one. Plus z1 squared z2 squared plus 2. This term now involves both these terms. There's a lot of terms that sort of multiply here, but it's z1 z2 z1 prime z2 prime plus z2. Sorry, I messed this up. This is supposed to be z1. Good call. Prime. So even I make mistakes when I start writing out long expressions like this. Plus z2 squared and then z2 prime squared. So just wrote out the inner product explicitly there. Now I'm going to group terms. And I'll write things kind of in an interesting way here. I'll write this as equals 1 plus, take out all the terms with a 2 there. Or rather, just these two terms, sorry. Plus 2 z1 z1 prime plus z2 z2 prime. Plus, that counts for these three. Now I'm going to factor it. This is a squared term, right? So this whole term here is just equal to z1 z prime 1. Make sure I get it right. Plus z2 z2 prime all squared. Right? Just do this out, you'll get each individual term there. So that's interesting, because this term here, right, is just z transpose z prime. It's z1 1, z1 times z prime 1 plus z2 times z prime 2. we can write this as 1 plus 2 z transpose z prime plus, this term's the same here, just squared, z transpose z prime squared, which is also a square term. That just equals 1 plus z transpose z prime all squared. The cool thing here is that computing this term, so this term is equal to this dot product of these big feature vectors, right? But we can compute it only taking the inner product in the original feature vector, original input rather. So remember, z is an n-dimensional vector. This is a k-dimensional vector. This requires k operations to compute this inner product. But this requires just n operations. And when n is much bigger than k, as is the case with those high-dimensional features, this is going to be a lot faster. I mean, I just proved it in this one case here. But more generally, this term, erase the equal there just to make sure it's, I'm not saying equals. This term to the d is actually equal to the inner product of the big feature vectors, where these big feature vectors are the entire polynomial feature vector of degree d. So this term is the inner product of two very high-dimensional feature vectors. Two dimensions that have dimension n plus d, choose d. But we can compute it in time that's only n operations. That's very nice, right? We're computing at this exponentially big or high-degree polynomial big feature vector here in times just order n. This is like the ultimate thing in computer science that you want to do, right? We have an order n algorithm for computing these very, very big inner products. To simplify the notation a little bit, I'm going to define this, and this comes up so much as inner products, that I'm going to define this as this kernel function k. So this is just notation. The inner product between two of these feature vectors here, z and z prime, I'll just call that a function k. So k maps from two Rn dimensional vectors and outputs a real number, where just defined by this formula, the number. And some particularly common kernels, one we already saw, one was the polynomial kernel. So this kernel here is computing inner products in a n plus d choose d dimensional space, doing it in order n time. This next most common kernel, actually probably the most common kernel, it's usually called a Gaussian kernel. Some people call it a squared exponential kernel because it doesn't have to do with actually a Gaussian distribution or anything like this. Like RBFs, it just sort of uses this kind of exponential form. But here, to compute the kernel between these two things, you subtract z prime from z, take the squared norm of that, negative squared norm, divided by some bandwidth sigma. So this should look a lot like an RBF, right? Where you're just using the two data points as the data input and the RBF center rather than a fixed set of RBF centers. But other than that, it's the same form. And you take the exponential of all of this thing inside here. And it turns out that we won't prove it here. This inner product dimensional feature vector. It's a feature vector of RBFs where you have an RBF center at every single point in your space. Don't worry about proving that, but it's sort of amazing in some sense, right? That this is an infinite dimensional feature vector. We couldn't even write it down no matter how much memory we had. Yet we can still compute inner products in this space. This one is not infinite. This one is just big, but finite still. This one's actually infinite. And remember, the biggest deal with RBF, the biggest problem is that as your dimension, n, grows, you have to kind of keep gridding your space in more and more dimensions, right? So that's sort of a tricky thing, because all of a sudden you don't have enough data to store all these different RBF, or sorry, enough memory to store all these different RBF centers. This is a way of saying, well, let's just put an RBF around every single point in our space. Let's not worry about choosing which points or which centers. Let's just put them around every center, every point, and use that as our feature vector. Now there, you can no longer have this trick of kind of picking a bandwidth. It's this, this very ad hoc thing I mentioned last time about picking the bandwidth using a certain mechanism. So you still have to pick this bandwidth here now for your inner product. But that's still pretty impressive that we can compute inner products in an infinite dimensional space with order n operations. Not even a high degree polynomial in n, but just order n. All right, so that's just right. He was kind of cool, right? That this is actually working. And we can do the high dimensional feature vectors, but so what, right? All we're doing is computing inner products here. It's not clear how we can actually use that for anything useful. But of course we can. That's why these are a big deal. So let's see how we actually go about using them. Now, the trick that lets us use these in optimization is, so actually let me take a step back for a second. Suppose now we have an optimization problem. So this is the form of a regularized sum of loss functions, right? This was kind of a very general form for the types of optimization problems we were looking at throughout this class, or throughout, certainly captured all these things, right? You sum over your data, you're minimizing over your parameters theta, the sum over all the data, the loss of this thing here is your prediction, and the true output, then plus, remember this regularization penalty on lambda. So we want the parameters to perform well on the data we have. We want them to also be small weights. Remember, for the polynomials, for example, if we force them to be small weights, we could have a high degree polynomial while still not overfitting to the data. So this is a very general form of optimization problem. And in fact, a lot of machine learning algorithms can be cast in this manner or something similar. The cool thing, the trick in some sense that lets us use these, or sorry, lets us use kernels in this framework. Remember, the kernel, I said, was what lets us represent high-dimensional feature vectors and take inner products. But we still have this kind of function here, right? It's not clear how we would still take inner products there, because theta is not phi of anything. Theta doesn't have to span that kind of space. So we're minimizing over theta, which in the case before could be infinite dimensional, right? How can we do that? It shouldn't be immediately obvious why you can do this at all. The trick we use here, or the fact we use here, is something called the representer theorem. This is actually a very limited form of the theorem. If people have ever seen optimization, this takes about 2 lines to prove, given some background optimization. It's actually a very simple form of it. The general theorem is quite a bit more detailed. But the essential idea is this. If we have an optimization problem of that form, so we're minimizing over theta the sum of some losses over m different examples, plus our regularization penalty on theta, on theta, then the optimal theta, the theta that solves that problem, will be of this form. It's the sum from I equal 1 to m, some number alpha I, which can be, finding these are, of course, the important part still, but some numbers alpha exist such that the optimal solution is equal to the sum over all our examples, alpha I times phi of xi. Remember, these are potentially infinite dimensional, and then of course so is theta. But we can actually find a more compact representation of this theta in some sense, because it's equal to a sum over all these alphas times the feature vectors, none of which we can actually compute yet. And for those that have seen some optimization before, this follows directly from what's called duality problem. So you basically, you set up this problem like this with an additional constraint, and the optimality conditions of the problem, the constrained problem, end up being actually that this condition has to hold. So we won't worry about that, about the actual, how that comes about. If anyone is curious and has seen these things, again, it takes about 2 lines to prove this very limited form of the theorem. But this is a very nice property here. So now we start to see why maybe this is possible to use infinite dimensional feature vectors. Because to represent theta in some sense, we don't need to store every entry of theta. All we need to store are these alphas. The alphas, in some sense, define implicitly what theta is, what the solution to theta is. So now, actually, I had this in a later slide, but maybe I'll say this first. The cool thing now is that, remember, our predictions were y hat equals theta, I guess in this case theta star, transpose phi x prime for some new input x prime. So, expanding this out a little bit, this equals the sum from I equals 1 to m. I had this in a later slide, but I think it actually is worth showing now. I'll probably try to rearrange these things a little bit. So our prediction, remember, all these things are still infinite dimensional. Theta is infinite dimensional. These are infinite dimensional. Or just 2 high dimensions to really represent. But this sort of prediction here is just going to be a linear function of these things. So this is equal to the sum from I equals 1 to m, just plugging this definition in, or this result in, rather, alpha I times phi x I transpose, because this whole theta is transposed, right? Transpose phi x prime. Which, of course, you know what this is. This is an inner product here. So this equals the sum from I equals 1 to m alpha I times the kernel function between xi and xi prime. Yeah?
So this notion of inner product, so the kernel function is going to output a different value than if I were to take the inner product in our normal definition of inner product, right? Sort of an approximation of this inner product?
No, the kernel function is the exact inner product between two. Why are there different kernel functions? Different kernel functions correspond to different choices of feature vectors. You can, of course, choose a polynomial feature vector that results in one kernel of degree d. That results in one form of kernel. In fact, it is the form that we had here. Right? If you choose to use a polynomial feature vector, you'll get this kernel. If you choose to use this infinite dimensional RBF, and you can't really use it, of course, but if you were to choose to use that infinite dimensional RBF feature that has an RBF center around every single point in the space, you'd get, this is the inner product. And so the choice of kernel is essentially choosing a feature representation to use. In that feature representation, though, this is exact, which is what makes it so cool here, right? Because the kernels are actually giving you the exact inner product, what you would get exactly if you were able to represent that big feature vector and then compute those inner products. Yeah, no, it's pretty cool. By the way, I prefaced last time before the lecture saying this would be the most mathematical, one of the more mathematical ones. That really was talking about the material in this section. So this is probably some of the more mathematical stuff we're going to cover in this course. So if it takes some time for you to go through it, don't worry. It is a little bit odd the first time you see it. You can actually do stuff like this. So yeah.
What exactly is M?
M here is the number of examples we have. So we have xi, we have m different inputs. Now that's actually very important, what the quantity m is. So remember, n is the dimension of the input, k is the dimension of the feature vector, and m is the number of examples, number of xi's we have. So x1 to xm.
So how does the feature vector look for Gaussian kernel?
Right, so the feature vector for a Gaussian kernel, what it is it's this infinite dimensional RBM. I could say RBM, I meant RBF. If I've ever said RBM before, that's something else entirely. It's a dimensional RBF. So remember, RBF features are features that have their feature vectors they're defined by a bunch of centers, right, a bunch of center points, and then by a bandwidth parameter. And so those are essentially, you have one entry in that feature vector for each different center. What the Gaussian, and you know, in some sense, it's good to think of it a little bit like this way, but you can also just think of it just purely in the kind of resulting form of what you get when you compute the kernel. But it's also good to think about what the feature vector kind of is in some sense. And what the feature vector there is it's, again, infinite dimensional. And for every point in the space, every potential point in the space, there's a corresponding entry using that point as the center of an RBF. So I actually don't want to draw it too much because, I mean, in some sense, if you had a one-dimensional input, right? I don't know if this will help clarify things or confuse things. What it will look like, actually, is rather than if you had one-dimensional input, and this was your input x, then you can kind of think of the RBF, or sorry, the Gaussian kernel as, rather than just a feature vector, kind of a feature function, actually, because it's an infinitely big and dense feature vector that actually is kind of like, you know, you have all these different RBFs around every single point in the space, right? But the ones that are close by are the only ones that have good value, and it ends up being exactly looking like kind of a Gaussian around x, this point. You don't have to think of it like that if you don't want to, but you know, each one of these would be a center, and the Gaussian evaluated here, you can kind of, you know, it doesn't really matter which way you do this subtraction here. The difference, the normal difference is the same thing. So these kind of end up looking like Gaussians themselves around the points. That's a very kind of vague notion there, and if it's kind of confusing, if this drawing was confusing, don't worry. It's actually not always important what the feature vectors look like. Oftentimes what's more important is just kind of the intuition of the kernel. So in another sense, the intuition of the kernel, well, I was going to get to this later, but the kernel can also be thought of as kind of computing a similarity between 2 points, right? So kernel values that are very big mean points that are similar. Kernel values that are small mean points that are far apart. And the Gaussian kernel says 2 points are similar if they're close in their distance, because then they'll be equal to 1, otherwise they'll be equal to 0. Again, don't worry about that. If that's also confusing, I'll try to explain a little bit of that later, but just trying to give some intuition, and if it's helpful, hopefully it will be helpful. Yeah?
Do you have an example for feature vector? Like maybe physical meaning or some other kind of practical meaning?
So I think the example I had was the quadratic function, right? So there are, a feature vector can be polynomial or monomial functions of the inputs, right? In that first example I drew. So that's one feature vector. Another feature vector are these RBFs. You take a bunch of center points And you construct these RBF functions evaluated at the input corresponding to each center point. So I'm not sure if feature vectors are just functions that take as input your input vectors and produce some usually higher dimensional output. And sometimes it doesn't really matter what they are. It just matters that they're somehow taking your input and computing some mathematical function on your input. And the difference in choice of feature vector determines the expressiveness of your function. So remember, in last class, we talked about polynomial features. And when you have a high-dimensional polynomial feature vector, you're essentially fitting, and say a one-dimensional input, you are fitting a polynomial function to those data points. And so the intuition of feature vectors is kind of about what kind of resulting function they produce. So polynomial feature vectors produce polynomial approximations. RBS produce kind of a local approximation where you have kind of local weights for each different centroid. And that's kind of the best way to understand them, I think. Okay, so the point of this slide, though, and I kind of went on a tangent here about how you use these predictions. The point of this slide, though, was that the resulting theta, which we now know how to make predictions from, so this seems like it could be useful, is of this form. So it is a sum of the different feature vectors, which we can also write as phi transpose alpha. Remember, phi here is our vector of feature vectors. So each row, so that was in R m by k, where each row x1 transpose was a transpose of the first one and the second one, etc. x2 transpose, etc. We just defined it this way. So if we want to come up with a sum here, well, we just transpose this again so that these things are the actual, so the feature vectors are the columns of a matrix. And then alpha is just going to be a vector of all our different alphas, which is going to be an Rm, because there are m different alphas. So this notation here is just an abbreviated form, a vectorized notation, just like we did for theta and phis. This is a vectorized form of our optimal prediction theta. All right. So now, what I've told you so far is that, first of all, optimal theta is of this form for some alphas. You can use that to make predictions through these inner products in high-dimensional feature space. I haven't told you how to actually compute these alphas yet. How do you solve this problem, actually find the resulting alphas that lets you, make those predictions? So that's the last ingredient in kernels, how do you actually make those things. And I'll just say, this thing here, this is the key to how you do this, how you solve those optimization problems. It really is just about this transformation here, and the rest is just a little bit of math. So once you have this fact here, you can solve all those problems and solve our big fancy nonlinear problems using this formalism here. Okay, let me go through it. And again, I think this is probably one of the trickiest parts of mathematically trickiest parts of the class. So bear with me. It's all coming back to sustainability and sustainable energy at some point, right? Because we're making these predictions about these things. But I know we're getting real mathematical, but it is very useful for such problems. So I do want to go through it. Okay, so I'm going to define a few things. Maybe I'll leave this up here, because this is sort of the key fact. So I'm going to abuse notation a little bit and define a kernel matrix K. So K was a function before. I'm going to call it a matrix now, where K is going to be an m by m matrix, where the ijth element here is really just for notational convenience. It's just going to be the kernel of xi and xj. Okay, just going to define that. And notice that this is exactly equal to, in our old notation, phi transpose. Right, because phi, the rows of phi were, I had this written before, but the rows of phi were these feature vectors. So the ijth element of this will be the ith row of this times the jth column of this, right? Because it's this transpose. So that's just equal to, well, phi I transpose phi j, which is equal to the kernel of I and j. All right, that's step one. It's kernel matrix like this. Maybe I'll write this up here too. And the important part here is that even though phis here are potential, they're m by k, right? So phis are potentially really a lot of columns in phi. That's the number of features that we have. And again, that could be infinite. So phis here, the matrix phi is infinite, potentially infinite, or just really big. Yet, we can compute this whole term here, because every element in this term is just equal to a kernel function evaluation, right? So we can compute them all. So we can compute this term here, even though we cannot compute or store phi itself. This is just like we could compute inner products in the space. We just couldn't compute or store individual feature vectors. OK, so we have k. We have this fact. Let's just go through least squares again. So remember least squares. In fact, regularize least squares. And in fact, I forgot to mention the homework. Shoot, let me stop a few minutes before class because the homework's out, but let me talk about that in a second too. But on the homework, you'll actually derive the solution to this in explicit form. And it's very easy. It's very much like the one we studied in class. But if you haven't seen it before, it's worth going through and sort of figuring out how to actually, making sense of all those manipulations that we did quickly on the board there. So OK, so we have this problem here. We have j of theta equal to phi theta minus y squared plus lambda theta. OK, let's go ahead and, theta is infinite dimensional here, but we know that theta, the alpha one, has to obey this form. Let's just go ahead and plug that form in to our equation here. This equals phi theta transpose alpha minus y plus lambda. And remember, the squared norm here, just this part here, equals also lambda theta transpose theta. I'll just write it out explicitly like that, rather than in this norm format. But plus lambda times, and do I actually have a lambda? No, I just have a lambda. OK, good. Plus alpha times transpose theta transpose. That's just theta transpose there. Sorry, not a transpose there. Right, because theta equals phi transpose alpha times theta, which is just phi transpose alpha. So I've written this just plugging in the fact that we knew our solution had to obey that form. So I'm allowed to do that, right? Now, the interesting thing here is what you'll notice, hopefully, is that the only way that phi appears here is here and here. That's exactly the form we had for what k equals. So these things are just k. So this just equals k alpha minus y squared plus lambda alpha transpose k alpha. So I got rid of all instances of phi and theta from this equation. It's still the exact same thing. There are no approximations here. But I, through some manipulations here, just got rid of phi and theta. So really, this is now, we could write it as j of alpha equals that. Now, let's just write out a couple things. Let's just solve this, essentially. So remember, this is one of the cases, because it's still least squares, it turns out you can still write the gradient, set the gradient equal to 0, as we did with the original least squares, and the solution will come out. So I'll expand this term. This is equal to alpha transpose, it's really k transpose k alpha. K ends up being actually symmetric, so k equals k transpose. And you can see that from this form here, that if you transpose this matrix here, it'll be equal to itself. So we can just write k twice, like that. Minus 2 y transpose k alpha plus y transpose y. Does everyone understand this manipulation I went through here, from here to here? This thing, remember, is equal to this transpose times this. This is what we use up there. And then we just distribute out each terms of that product. So I'm just abbreviating that a little bit there. And then we add regularization here, which was lambda alpha k alpha. Okay, now we take gradients and we get that. These are just playing our rules of gradients we saw last time. It's exactly the same as least squares derivation. I won't. It's might look a little bit more complex, but it really isn't. It's exactly the same thing. So remember, this is that something transpose a big matrix times that something, and the gradient there is just going to be 2k alpha minus k transpose y. Sorry, 2k transpose y. This doesn't depend on alpha at all. And this term is going to be plus lambda k alpha plus 2 lambda k alpha. So just look at the gradient here. And now, as before, we set this equal to 0. And we solve for alpha. And the resulting solution is we can multiply through by k inverse. K may not be invertible here, so we're not actually quite doing that. We're actually just saying the fact that, well, this has to lie in the right span, and that's actually OK to do that since there's a k in front of everything. So as long as this term, basically as long as this term, 2k alpha minus 2, sorry, this is just k, there's no k transpose there, minus 2y plus 2 lambda alpha. As long as that term is equal to 0, so will this thing be. Because this is just equal to 0, you multiply it by k, it's still equal to 0. And this one here implies that alpha equals k plus lambda I inverse y. OK, so slide of relief. That's it for the manipulations. And you'll go through some of these too, so hopefully it'll be drilled a little bit by the homework. But the point here is that we've found those alphas. We found the alphas for theta star here. These are the ones that minimize that least squares objective, again, by computing gradients, setting it equal to 0. We find that alpha, and I'll say alpha star here, alpha star has this form. So again, this does not depend on phi or theta at all. It's just our kernel matrix, which is all the possible inner products, plus lambda I inverse times y. All things we can compute. Yeah?
How do you know that's invertible?
So k might not be, right? But k plus lambda I actually always will be. And the reason you know that is that kernel matrices are what are called positive semi-definite matrices. If you haven't seen this before, it's a little bit in the notes of linear algebra. It means that all the eigenvalues are greater than or equal to 0, this matrix. And the way you know this is that it's of this form here, which is asymmetric positive definite matrix because it's something transpose times something else. And that has to be positive definite always. It's positive semi-definite. So k is positive semi-definite. If you haven't heard the terms before, don't worry. You won't be required to know why this is true. But if you add some multiple of the identity times a positive definite matrix, you're adding lambda to the eigenvalues. Those eigenvalues will all be bounded away from 0 then. And so this will be invertible. So basically all it means is that you can, in fact, always compute this. And when you plug this into MATLAB, it won't freak out. It'll give you the solution. And in fact, this is necessary because remember our issue, one of our issues with big feature vectors was that, well, we started to have this too much representational power, right? We could always represent a function arbitrarily well. So if you have an infinite dimensional feature vector, well, that's going to be pretty representative of, that's a pretty powerful function, right? You probably, and in fact, if you don't add anything here, what you can see, maybe it's not obvious, but it might not be obvious, but this will always match the input exactly if you don't add any regularization here, assuming k is in fact invertible. So what this means is that because we're working with great big feature vectors here, high dimensional polynomials, infinite feature vectors, we need to really think about some regularization. Otherwise, we'll just have too expressive of a function, and then we can't get solutions. So in fact, adding that lambda I there is actually quite important here. OK, so as I said, this part was what I was thinking about last time. This part is probably some of the most intense math you'll see all semester. But this is incredibly useful, these type of methods here. They're used all over the place, and they're incredibly powerful. This is actually the slide I had that I should probably put earlier, but basically it's just saying that once you find that thetas, you can compute predictions on new inputs using just the kernel function. Right? This is what I wrote before. Because you take your things that are both infinite dimensional, you expand them out by the form of it, and then you get that. Now, there's one point to keep in mind here. Actually, a couple points I want to make. The first is that in order to make a prediction on some new example, so we get some new example x prime here. To compute our prediction, y hat prime, we have to compute the kernel between all our examples and this new input here. What that means is we have to actually keep all our examples around, right? We have to keep them stored somewhere so that whenever we get a new example, we can compute all those kernels and compute that function. This is in contrast to linear regression. One nice thing about linear regression was, in the normal form, or the standard form, is that once we had theta, we didn't care about keeping our examples around. To compute a prediction, the prediction is just theta transpose phi of x prime. So we could just throw away all our data. Wouldn't matter anymore. The only thing that matters about the data is how it creates the resulting theta. Here, every time you want to make a prediction, you have to compute this kernel. And this kernel between every example you have and the resulting one. At least if the alphas are not equal to 0. And that does come up sometimes in some cases where you will try to encourage them to be 0. But assuming that's not the case, you'll have to do this. So this is what makes the method called a non-parametric method. This terminology, people, I don't want to define it loosely here because it means something very specific. But essentially, machine learning methods are divided into two classes. Well, a lot of classes, but one categorization is between parametric and non-parametric algorithms. And this does not mean they don't have parameters. But what it informally means is non-parametric methods are methods that don't have a fixed number of parameters. The number of alphas you need will actually grow with your size of your data set. And you'll have to keep, in some sense at least, and again, this is being kind of informal, but in some sense, you have to kind of keep all the old examples around, always in non-parametric methods, rather than you can't just throw them away and just trust your one set of parameters anymore. OK, that's point number one. This is what's called a non-parametric method. The second point, actually, I don't think I have a slide on this. Let me just make sure. Right, OK. I have a slide on this, but the next point is K here is, remember, K is an M by M matrix. Every element of K you have to compute, and it has to be computed through this kernel function, right? So for every example in your data set, this is just to train the method to find the parameters alpha. You have to compute this kernel function between xi and xj for all I and j. M by M matrix. And furthermore, you have to invert it. You have to invert an M by M matrix, at least for this kernelized least squares function here. You have to invert an M by M matrix. Now, if you know sort of about complexity of things like inversion, inverting matrix costs order n cubed, where n is the size of the matrix, right? So here, this operation is going to be, I think this is just kind of an aside, but it's important to keep in mind. It's going to be an m cubed operation here. And that, when we talk about the trends in machine learning being things like big data and lots of examples, and you want to release a lot of these things, this makes it tricky here, right? Because you have to invert, maybe say m is 100,000. Well, no single computer, at least right these days, can invert a 10,000 by 10,000 matrix. It just can't even store it oftentimes. So there are limits to this. You pay a price for this representational power. Sure, you might be getting a net win because your number of features is even bigger than that, even bigger than m, so you're actually winning here. But there are prices to pay, too. OK, so this is all a little bit, I think, somewhat abstract. And this will hopefully become more concrete when you actually do the homeworks. But for those homeworks and in general, the code here could be quite useful. So this is how you actually would go about computing kernel functions and kernel regression in MATLAB. So a lot of math here, but really it ends up only being a few lines of code to do all this. So this is a polynomial kernel of degree d with some number of some size input. All right, let me just define what all these terms are here. So one thing you could do, right, and this is a common trend in MATLAB, is that you have your input data, right? You have an xi for all your, let me check what time it is. You have an xi for all your different input points. And you could just go ahead and element by element construct that kernel matrix, right? You know, say for basically for I equals 1 to m, for j equals 1 to m, k I j equals, say, 1 plus x. I guess it would be something like this, right? It would be, I'll just write it here, xi, xj transpose to the d, where you do this correctly in MATLAB. And that would be fine, but MATLAB ends up being kind of inefficient at things like this when you write out those for loops explicitly. And it's much better if you can to actually do this kind of in one big shot. Do it all at once. And you can actually do that here. You can compute this entire kernel matrix in one call in MATLAB. This is true for the Gaussian kernel and for the polynomial kernel. And the way you do it is you create a big X matrix. And big X is just like big phi, except it has X vectors in the rows instead of the phi vectors. So this is going to be a vector or a matrix in M by N, which is equal to x1, x2, x1 transpose, x2 transpose, da, da, da. OK? And that's this X matrix I'm showing here. Now, what you can hopefully convince yourself of is that X transpose is a matrix of all these inner products here. So X transpose ij equals xi transpose xj. So I take this whole thing, XX transpose, which is what I'm doing here. That is a big matrix, an M by M matrix of all the inner products that we have. Then I just add 1 to it. And when you have a matrix adding to a scalar, MATLAB will add 1 to every item in that matrix. And then I'm saying take this whole thing to the d. And this dot to the means element-wise, you raise each thing to the dth power. So what this does is this is doing this thing exactly, but in just one line of MATLAB code. Again, you'll sort of figure this out as you play with it. So what I would recommend is on the homework, you'll have to compute this kernel. Try it out. Try it both ways. You know, try it this way if it makes more sense at first, and then try doing it all at once. And now we solve for the alphas here, just again using our little backslash. Backslash is just kind of like an inverse, but even when the matrix is square, it still can be more efficient to use backslash sometimes for sort of technical reasons. And so these, and really just these two lines of code, right? Because everything else is just setting up the parameters here. These two lines of code solve everything we talked about today. Right, and 2 lines of, not many characters either. They're pretty short as MATLAB code goes. This is why MATLAB is, for all its faults, is a wonderful tool for this kind of methods. OK, so now to actually make a prediction, though, we still need to do something, right? So we take a new vector, x test, which is our new data point. We have some new data point we want to make a prediction on, which I'm calling x test. I guess here x test would be a row vector corresponding to some, x would be basically x prime transpose. And we do the same thing. And this just computes the same kernel between all our training data and this new example. Right? Because we have to do that. Remember, we have to compute kernels between, whenever we want to make a prediction on a new point, we have to compute those kernels. So this line here computes those kernels for all our data points. Again, you could do this element by element by just computing individual kernels, but this is a little bit faster. And then y hat here is just going to be this kernel, which is kind of actually, it's sort of a vector of all the kernel evaluations, times our vector of alphas. So that's equal to exactly, again, theta transpose phi. but without ever having to compute theta or phi. They're all implicit in the alphas here and in the kernels. This same trick about doing it all in one line you can do with a Gaussian kernel. I'm writing it, it's a little bit simpler if I just write this function square dist here, which computes pairwise distances between a whole set of two different sets of matrices. That function, you can look at it. It's included in the homework, for example. So you can just use that function square dist. But then you just do exactly what we did before, right? Basically compute distances between all corresponding points here. That's the Gaussian kernel. Divide by sigma squared and multiply by negative 1/2, and then take the exponent. And that is now going to be a matrix of all for your entire Gaussian kernel. Again, you can compute it element by element. Here's one line that actually does it, in the same line for computing the alphas here. Now, it's important to know that, of course, if you use a Gaussian kernel to train the thing, you have to use that same kernel when you're making predictions, right? You can't, otherwise those don't mean anything. They're just random. So make sure that you use the same kernel on a test example as you did when you constructed your alphas. OK. That's the second to last slide. And no, sorry, I think I have a few more. So these are just some examples of what this looks like. And as you would imagine, hopefully, it looks exactly like polynomials and RBFs. And this is a 1D case, right? So here we're not in that high dimensions yet. You can compute these all explicitly. But this is just sort of showing you that you get the exact same types of results. So this is, for example, polynomial, nonlinear regression, fitting a polynomial function of degree 4. Again, with some lambda here, they have to pick. Otherwise, it'll be hard to solve these things. You would never know whether this was a kernel or a explicit features unless I told you, because it looked exactly the same. It is the exact same thing. It's computing these polynomial feature vectors. And other than a slight difference in the regularization, because you have these interesting kind of constant factors in your feature vector for the polynomial kernel, but it's not a big deal here, you're getting the exact same thing. And this is degree 10, and it looks just like degree 10 we saw before, essentially. A regularized degree 10 polynomial. And same with the Gaussian kernel. This looks essentially just like our explicitly RBF feature vectors when we regularized a little bit. And this is for a very small bandwidth. So they're sort of very narrow bumps in the space. And this is for a very wide bandwidth. So for smoother RBF features. And this is a pretty nice fit to the data, right? I mean, you're starting to see these things do quite well at explaining data like this with really without much tuning, right? I mean, I didn't tell it anything kind of about this function, I guess, other than I just sort of picked sigma equal to 40 because it ended up looking nice. But it's a pretty kind of easy way of getting very nice fits to data like this without worrying about what degree polynomial is that and all these kind of things.
Is there any way to compare which one is doing better between the first and
Yes, so that's what we'll talk about, not next time, but the next time after that. So in some sense, all these fits we're talking about the data thus far, we're just talking about minimizing some loss function on the data that we have, right? And then, as I mentioned before, the problem there is that more expressiveness and more higher degree polynomials, smaller bandwidth actually, these always lower the objective function. They make a more explicit function, so they let us have a lower and lower cost. But there's a sense in which this is not right? Because this is not a good fit anymore, even though it has a lower cost. And we'll talk about evaluating which one is actually a better fit, which is a hugely important part of machine learning, right? How you actually evaluate these things. When we talk about evaluating machine learning algorithms, that'll be the 4th set of slides on machine learning after classification. Because absolutely, yeah. You want some way of saying this is a better fit than this, or that's a better fit than that. And the way you essentially do is you have training and testing sets that you hold. So you hold out some of the data, train the system on some of the data, and then evaluate its performance on other sets of the data. That's the basic idea, but we'll talk much more specifically about what you do with that. So again, here's our canonical problem, though, and we'll talk about how you exactly can evaluate how well your energy prediction there matches up with some training and testing set. All right, final note, and then we'll end on this. This is the end of the slides on kernels. Final note is that what I derived right there was the least squares, so squared error, squared loss function, the analytical solution for this squared loss function. And as we know, that's not the only loss function we might want, right? Last time we talked about all these other loss functions we could have. So the question is, can you do the same thing with those? Again, it's not obvious, right? Because, well, you can't plug it into that analytical formula anymore and come up with everything as the way it was. But the important point is that represents your theorem. That fact of the form of those alphas remains true for any, at least convex, and actually I think it's true for, in some sense, for any loss function, but we'll talk about being true for the loss functions that we'll consider here. That's true for any loss function. So for any loss function that we'll talk about, you could always make this transformation from theta to phi transpose alpha. And when you plug that in, remember, oftentimes we'd have a form phi theta in our objective function. And so this just turns into k times alpha, right? Because you plug in that assignment for theta there. So it's exactly the same in some sense. And again, using the fact that we can do things like YALMIP, or we have tools like YALMIP, you can actually solve them very easily once you know this transformation. So remember, the absolute loss, for example, all you would do, and you want to add some regularization too, you do this in practice, but all you would do is you take your absolute loss there. Before, this was phi times theta minus y, was what we wrote to solve this. Now you just write k times alpha, and have alphas be your variables instead of the thetas. And that's all it takes. And that kind of, I think, exemplifies hopefully the simplicity, in some sense, of these things. That you do have to go through some math to realize what's going on here. But once you have all that background, you can plug these things in very easily and very quickly get a very powerful form of nonlinear regression that lets you do kind of a lot of very complex and powerful predictions in this framework here. And as I said, there's all sorts of loss functions you can use here. So, and they go by weird names too. So if you use this deadband loss, which is this an epsilon range that suffers zero loss, and you use kernels, well, people call that support vector regression for reasons that kind of make sense historically, but that's all it is. So a lot of algorithms in machine learning, and very advanced ones, come out exactly in this form. And we'll let's cover some more of those in the homework. OK, so I believe I'm out of time. We're done with this lecture. The last thing I want to mention, I guess we have 2 more minutes. Last thing I want to mention is the homework. The first assignment is posted, both the homework and the data. It's on the website. It was there before class started. Take a look at it. It's due 2 weeks from today at the beginning of class. Again, there's that late policy you can read about and the policy on collaboration. You guys can collaborate to work on it. Please do come to office hours to talk about it. I'll also have double office hours the week before it's due, the week that it is due. So you can come on Mondays and Wednesdays too. And I might even have longer than just an hour. I know people like to come to office hours, especially when homework's out. So if you're doing the homework, the goal is this should take about, I mean, they're meant to be hard. There's 4 homeworks. That's sort of the main thing of the class other than the final project. They're meant to be hard. They're meant to be challenging and to kind of reinforce a lot of what you've learned here. You should take about 15 hours is sort of the time frame I'm shooting for to complete the assignment. If it ends up being a lot more and you're doing the 8:30 class, you might want to consider shifting down to the 6:30 class if it starts taking 40 hours to do this or something like that. You don't have to. You can still go for it if you really want to put the time in. It'll be great and valuable. But do keep that in mind. And if it starts taking a lot of time, even in the 6:30 range, then come talk to me because there probably is some kind of clarification I can make that should make it take about that amount of time. So anyway, we're out of time now. Good luck. come to office hours on Monday if you have any questions.
Good.